Hey there, folks. We are looking at Euler's method. Hope you're having a great day today. And we're going to use Euler's method to approximate solutions to differential equations. Now, so remember, you have the derivative. Euler's method is a numerical approach to approximating the particular solution of a differential equation. And Euler's method uses the concept of local linearity to say that the function behaves rather like the tangent lines at a particular location. And we're going to use that to approximate the shape of a solution curve. We're going to use the slope of the curve to create short connected line segments that kind of simulate what the graph would look like. Now, we want to use slope at x sub 0, so you can kind of see here at x sub 0, so we're going to use the slope of what that would be. Let me draw a real quick tangent line. So you see the tangent line would be kind of like that. And then we've got this delta x that we want to consider. We want to say the length of the segment is predetermined. We say, okay, I'm going to make it really small. I'm going to make it, say, 0.5, 0.1, or whatever it is, but you're going to make it small to consider a step size for delta x. Then the next segment from x1 to x2 uses the slope at x sub 1 to find the next point in x sub 2. This process continues until you reach the value that you're trying to find, say approximately f of 1.4, given that you start at 1. Okay, so you can see I kind of have it laid out here. Let me get one more thing here, like this is a delta x here along the x-axis. So you see the y-axis is up here. And you can see in the picture that you have, it's an approximation of the curve, but it diverges, and that would be remedied by making delta x even smaller, okay, just to show you how it works. So how the process continues until you reach that. So you start off with point slope form, and you can see that if I have y sub 1 and I want to find y sub 2, I'm using point slope form, and I'm going to solve for y sub 2 in this. But if you notice, the delta x is always going to be the same. X sub 2 minus x sub 1 is going to be delta x. X sub 3 minus x sub 2 is going to be the same delta x. Okay, so we have that, and then we've got y2. Then I can replace x sub 2 minus x sub 1 with delta x. And keep in mind the slope, that m is going to be the slope of the tangent line at a different point, so that's going to change. So now I have y sub 2 is equal to y sub 1. I'm going to put a little tail on this. Y sub 2 is equal to y sub 1 plus m times delta x. And we have to evaluate dy dx at the point x sub 1, y sub 1. So when we do that, and sometimes you only have an x, or sometimes you only have a y. So now we have y sub 2 is equal to y sub 1 plus delta x times dy dx evaluated at x1, y1. And then in the last step here, all I did was say, well, it doesn't matter what it is. Y sub 3 is equal to y sub 2 plus delta x times dy dx evaluated at x2, y2. So we're just going to leave this as an n expression here. Okay, so that it's always the n plus 1th term, the y value, is equal to y sub n plus delta x times dy dx evaluated to x sub n, y sub n. Okay, so there's our formula coming right from our good old point slope form. Now, in the smaller the step size, the better the approximation will be. The approximation will be an overestimate if the curve is concave down, and an underestimate if the graph is concave up. So if we have information about the second derivative, that'll always be a little bit helpful to be able to look at what's the sign going to be. So if what's the sign of the second derivative? So if it happens to be negative, then the graph is concave down on an interval. And remember, we're starting out, we have dy dx. We want to find y. So sometimes, we can't get the function, but we can get the second derivative. So there you have it. There you go. Let's look at the first example. Let y of x be the particular solution to the differential equation, so a particular solution to the differential equation. And if you notice, the differential equation is given y prime is equal to x minus y. So you can't separate the x's and the y's here because there's a difference. With initial condition, f of 0 is equal to 1. So that gives us our starting place here. So that gives us our starting place. Use Euler's method to approximate f of 1.5 using 5 equal step sizes. So remember, we're going from 0 to 1.5 here. So from 0 to 1.5, we take that 1.5 and we're going to divide it by 5, right? So we have b minus a is then equal to b minus a over n is 15 minus 0. So you see that 15 minus 0 is going to end up equaling 0.3. So that's a pretty small, not super small, but it's a small value for delta x. So we have delta x, so we start off y sub 1. We have y sub 1 is equal to y sub 0 plus delta x times dy dx, and that dy dx is evaluated at 0, 1, the point where we start. So we just start plugging things in where y sub 0 is 1, delta x is 0.3, dy dx, we just plug in our 0 and 1, and we get y sub 1 is equal to 0.7. And then we go put that in the table up here. Y sub 2, and we keep doing this. Y sub 2 is y sub 1 plus delta x times dy dx, but that's now evaluated at this 0.3 and 0.7. So then we bring our y sub 1 down, is 0.7. Delta x is still 0.3, always 0.3 on this problem. And then x minus y is going to be 0.3 minus 0.7. Okay, and we get a value of 0.58. Okay, there's our y sub 2. Put that in the table, 0.58. So now we're at 0.6. Okay, so y sub 3 is y sub 2, which is 0.58, delta x, which is 0.3, times dy dx evaluated at 0.6. So it's 0.6 minus 0.58. So it turns out we get y sub 3, turns out, and you can see that it's the values go from 0.7 to 0.58 to 0.586. It's kind of interesting. You almost don't expect it to go back up a little bit, but it does go up just a tiny bit. And then we get 0.586 here. And then we go from 0.586 as it gets bigger. Well, it's getting a little bit bigger. It didn't go down. So then we have y sub 4 is equal to y sub 3 plus delta x, which is 0.3, times dy dx, which is 0.9 minus 0.58. And then it turns out we get 0.6802. So as the values are getting bigger, we start off at 0.7, but it then goes to 0.58, 0.586, 0.68. So you kind of wouldn't expect it to go down and then go back up again, but that's really what's happening with this. It is 0.6802, and here we have that value. So then we plug that value in. We're going for y sub 5. So we get y sub 4 is 0.6802, delta x is 0.3, and then we evaluate x minus y at 0.12, 0.6802. And we end up with 0.83614, and that is our approximation. So if you were on the AP exam, you would probably say the approximation for f of 1.5, it's going to be approximately 0.836. I think yep, that would be what it would be then. Okay, and there you have it. There you go. There it is. Okay, one more problem that you have. I'll let you look over this. Pause your video if you need to. Is this last one, example 2, where you have dy dx is equal to 2x plus y. Again, you cannot separate the values. And so you have, the first step is, it says approximate using Euler's method using 4 equal step sizes. You're starting at 0 and you're going to 1 here. Oh, I'm sorry, you're starting at 1, my mistake, and you're going to 0. So that means you're going backwards here. So given that initial value, you want to find y of 0, approximate y of 0. So there's the answer you're looking for, right? Okay, so starting off getting the step size, you know that you're going backwards 0.25 for delta x, okay? So you're starting at 0, you're starting at 1 and you're going to 0. Okay, so you can see your values there. Now, you have in your calculator a way to do this, and I'll show you when you get back to class, because it's very quick and you can get these. Once you set everything up correctly, there's an iteration factor in your calculator where it just like once you plug it in, some of you that are interested, you may want to look Euler's method with the TI-84. You can see online. There are different ways that you can do it. But we start off at 1 here at this value. And then we've got, let me go back to this. So we've got y sub 1 is equal to y sub 0 plus delta x times dy dx evaluated at 1, 3. But remember, your delta x has to be negative, okay? So you've got negative 0.25 here for delta x, and then you have dy dx evaluated at 1, 3 is going to be 2 times 1 minus 2 times 1 plus 3. And you get y sub 1 is equal to 1.75. That goes in the table for 1.75. And then you're going to start over again. I think I'm going to do one more of these. So the fourth step then is that you have y sub 2 is equal to y sub 1 plus delta x times dy dx. And then you're going to evaluate that. At the next point is, instead of 1, 3, it's going to be 0.75 and 1.75. Okay, so you have y sub 2 is equal to y